So today I am going to talk about Banach space. Okay. First, recall something. Recall. X. First, let me fix something. Whenever I am saying a field F, it is basically R or C. Okay. Now, X, a vector space over F. I am giving a norm, the function from X to F with the property 1, norm of X equals to 0, if and only X equals to 0. Basically, not field actually. It is a map from X to.
Its screen is not available.
Screen is not available. So that is true. Is it visible now?
Yes, sir, visible.
Second property is norm of Cx equals to mod C into norm of X. And the third property, norm of X plus Y less than equals to norm X plus norm 1. Here, C belongs to F and X comma Y belongs to X. Okay. So this, a vector space with a norm is called a norm linear space. So we will say that this X comma norm is called normed linear space. Now today we'll going to start Banach space. Okay. Banach space. So definition. Okay, now our setup is basically whenever we are talking about Banach space or anything, so we will set that X comma norm is a norm linear space. Norm linear space. So now, what's the definition? So if X is complete with respect to the metric T, where everybody, I think everybody is familiar with the definition. What is the meaning of a complete metric space? Can someone tell me the definition? What is the definition of complete metric space? What is the definition of a complete metric space? You guys have to say something, otherwise I will not understand how much I have to talk or how much I don't have to talk.
I think in which every sequence converges, convergent sequence.
No. Think about little bit. What should be the definition of the complete metric space?
Every Cauchy sequence is convergent.
Okay. Here is the definition. A metric space is said to be complete if every Cauchy sequence is convergent. Okay. So a nonlinear space is Banach space when it is complete by the metric T, which is basically we are getting from the norm. Okay. So our first example of a nonlinear space is basically very our known vector space. R. It is the basically the mod on R, distance from the origin. C. Okay, this is the examples of complete nonlinear space. R and C are vector space, and the mod is whatever mod you know, the distance basically. Okay. Now we can say that Cn and no, what is the norm at here? Here the norm is for Z1, Z2, Zn belongs to Cn, norm of Z1, Z2, Zn okay. Now we can talk about okay. Now I am giving a proposition. Okay, so in R or C, so we know the what is the meaning of convergence of a series. Okay, so now in a nonlinear space, there also there is also meaning of convergence of a series. Okay. Now definition. X nonlinear space. and xn a sequence in x. We say the series summation xn converges. That means there exists S belongs to capital X such that epsilon greater than 0, there exists n naught belongs to natural number such that for all n greater equals to n naught, summation xk k equals to 1 to n minus s, its norm is less than epsilon. And 2, we say the series summation xn converges uniformly if summation norm of xn converges on. Okay. Now, there is a proposition. What is it? What the proposition tells us? A nonlinear space X is Banach space if and only if every if and only every absolute converging series is convergent. So what will be the proof? Okay. So first, suppose take us what can I say? Okay, let me define something first. Suppose xn a sequence in x, so Sn is basically defined to be summation xk k equals to 1 to n. Okay. So now, so this side, X is Banach space. And Xn, let Xn a sequence in X such that summation norm of Xn exists. So we need to show, what we need to show? To show summation xk, sorry, summation xn n equals to 1 to infinity exist. How we can show? Okay. So what I can say now, as summation norm of xn is less than infinity. That's mean. So our main idea is I want to show this Sn. Sn is basically, I will show the sequence Sn. Sn will be a Cauchy sequence. As X is Banach space, if Sn is Cauchy, then it should be convergent. That's if I can show Sn Cauchy, then it will convergence. Hence, the series summation Xn is convergent. That's my idea. I will prove by using this information that summation of norm of Xn is convergent. So need Cauchy I need to show. So let for epsilon greater than 0, there exists n naught belongs to natural number such that for all m greater than n naught, what we can say? Summation norm of xk equals to 1 to m minus summation norm of xk equals to 1 to n less than epsilon, which implies norm of less than epsilon, which implies summation this thing is less than epsilon. Now, less than epsilon by triangular inequality. This implies Sn is Cauchy in X, which implies limit n tends to infinity, Sn exists. Hence, we can say summation xn n equals to 1 to infinity exists. Is it clear? Anyone have any doubt? Just tell me. Is it clear to everyone? Tell me if there anyone has any doubt, please let me know.
Sir,
Tell me.
explain this from for epsilon greater than 0.
What?
This summation k1 to m minus k1 to n less than epsilon.
Okay, this part for epsilon greater than 0, there is n naught belongs to natural number such that for all m greater than n naught. Then
Yes.
I have written a line. You haven't get from how I write that line, right?
Both are less than epsilon.
Both are less than epsilon. I don't get it.
Norm of summation k n plus 1 to m xn less than epsilon implies this is less than epsilon.
How I write from there to there, right? Your question. It is more. Okay,
Yes,
yeah,
sir.
it is more.
Yes.
It's more. It's not the number. Sorry, it was my mistake. Okay, now for the second part, what it is given? It is given that every absolutely convergent series is convergent. It is given. Series absolute convergence is convergent. Okay. So what we have to do? So now let xn is Cauchy in x. So I need to show this Cauchy sequence is convergent. For that, what strategy I am going to use? I will show this Cauchy sequence as a convergent subsequence. Then we are done. If a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself a convergent sequence. Okay. So look carefully. There will be a construction. How I construct a convergent subsequence by giving this information, and try to remember this construction, because in sometimes in functional analysis we are going to use this kind of construction, not the same one, but this kind of idea will you will have to use for by using some bound kind of things. You will get it what I am going to say. Okay. So what can I say? Suppose you take epsilon equals to half. Okay. So there exists n1 belongs to natural number such that for all n greater than n greater than n1, we can say xn minus xn less than half. Okay. So it is true for we can wait a minute. We can also use the equality at here. It is not a big deal. So we can say that N1. Okay. Now leave this. Also similarly, for epsilon equals to 1 by 2 square, there exists N2 choose greater than N1, comma N2 belongs to natural number such that for all M greater equals to N greater equals to N2, norm of xm minus xn less than 1 by 2 square. Okay. Now, this N2 is greater than N1. So we can write at here that by using this, we can write this that norm of xn1 minus xn2 less than 1 by 2. Okay. And for this case, also we can say that norm of xn2 minus norm of xn greater less than equals to 1 by 2 square for all n greater equals to n2. So by using, again I will take epsilon equals to 1 by 2 cube. So by this construction, we are by the, and so on. I will use this process again and again. So after this thing, what I will get that there exists x nk subsequence of xn such that norm of xnk minus norm of xnk plus 1 is less than equals to 1 by 2 to the power k. Okay. So what can I say now? Hence. So so now watch this. So summation norm of xnk minus xnk plus 1, this norm k equals to 1 to infinity, if we take, it is basically less than equals to summation 1 by 2 to the power k equals to 1 to infinity. This is finite. So this series is, so what can I say? This series is absolutely convergent. Hence, it is convergent. So what can I say? Summation k equals to 1 to infinity xnk minus xnk plus 1 must be less than infinity. Okay. Now, when we are talking about the convergence of series, we are talking about the sequence of partial sums. So, what is Sk? Sk is nothing but summation xni minus xni plus 1 I equals to 1 to k, which is nothing but x n1 minus x n k plus 1. So now limit sk exist, which implies limit k tends to infinity xn1 minus xn k plus 1 exist. Now xn1 is a fixed term. That's and the difference of xn minus 1 xn1 minus xn k plus 1 exists. What that implies? That implies hence limit k tends to infinity xn k exist. As summation sequence x is Cauchy and its subsequence xnk convergent. Which implies xn is convergent. This makes that this is a Banach space. X is a Banach space. Is it clear? Is it clear? Tell me. If anyone has problem with this group, please let me know. Okay. So now we are going to start about the what is the okay. So we have talked about norm. From that we have got a metric. Now we are interested on what are the continuous functions look like on a non-linear space. Give me a moment. Now we are going to start bounded linear operators. First, let's fix some notations. This nonlinear space. For x belongs to x, r greater than 0, b of x comma r equals to y belongs to x such that norm of x minus y less than r. and it is defined by this. It is basically open wall of radius r and the center at x. And by this, we are defining basically the closed wall center at x of radius r. So basically, there is a notion of uh, what I can say, uh, continuity. Now, particularly, we are interested on if a linear map from x to y is continuous. So, what is the basically equivalent conditions? What is, if we want to check the continuity? Always we need to check the definitions from we are getting from epsilon delta or the uh, pre-image of open set open or the some results of topology, or there is an easy way to check whether a linear transformation x to y where x and y are non-linear space is continuous. So let's try this. Okay. Okay. First theorem. Let x comma y are non-linear space. And t from x to y is linear transformation. Then following are equivalent. First, t is continuous. T is continuous at a point, continuous at one point of E. T is continuous at 0. For there exists m greater than 0 such that supremum of norm of tx is less than m, where x belongs to where norm of x is less than equals to 1. Okay. And of course, phi t is uniformly continuous. Continuous. So one implies 2 is trivial. Okay, please someone try 2 implies 3. Please, someone please try the 2 implies 3. Please someone try this. Okay, let me try this. Okay, so proof. So 1 implies 2 is basically the definition of continuity. Basically, definition of continuity. Two implies 3. How can we say? Okay. So let T is continuous at x belongs to x. Now I need to show that x is continuous at 0. Let xn sequence in x such that xn converges to x as n tends to infinity. Sorry, mistakes. Xn converges to 0. Hence, we can say xn plus x converges to x as n tends to infinity. Now, this sequence converges to x and t is continuous at x. This implies t of xn plus x converges to t of x as n tends to infinity, which implies t of xn plus t of x tends to tx as n tends to infinity, which implies t of xn tends to 0, which is basically t0 as n tends to infinity. So hence, t is continuous at 0. Now, how 3 would imply 4? But they are saying that if t is continuous at 0, then it should be so the supremum of norm x less than 1, norm of tx is basically is bound. Okay. So we are going to do in this way. And so what this is given that t is continuous at 0. So then epsilon equals to 1. There exists delta greater than 0 such that whenever norm x less than delta, then norm of t of x is less than 1. Okay. Now, so what can I say? For y not equals to 0, take x equals to delta by 2 y by norm. So if you calculate, the norm of x is less than delta equals to delta by 2 less than delta, which implies t of x is less than equals to is less than 1, which implies that norm of t of y by norm y is less than delta by 2. So which implies supremum of norm of T of x such that norm of x equals to 1 is less than del by 2, which will implies norm of Tx is less than del by 2. By the exercise which I am giving right at home, that exercise is supremum of norm of Tx, norm of x equals to 1, equals to supremum of norm of Tx, where x is less than equals to 1, equals to supremum of norm of Tx by norm of x these three are same. So using this exercise, I can say that supremum of norm of Tx, where x is less than norm x is less than equals to 1, is less than delta by 2. So that's why 3 implies 4. Now 4 implies 5. So they are saying there exists m greater than 0 such that supremum of norm of x less than equals to 1, norm of Tx is less than m. We need to show that T is uniformly continuous. Okay. Then take x comma y belongs to x such that x not equals to y. So x minus y by norm x minus y has norm 1. Okay. So what can I say that? Hence, norm of T of x minus y by m, which implies norm of is less than m norm of x minus y. This inequality gives that T is also, I can write in this way also, that norm of Tx minus Ty less than m of norm of x minus y. This inequality tells us that T is uniformly continuous. Okay. And if T is uniformly continuous, then T should be continuous, hence we are done. Uniformly continuity implies continuity. This is the equivalent condition. So in these equivalent conditions, the most important one is basically this number 4 condition. In whole function analysis, the 95% strategy, the 95% procedure how to show T is continuous is by in this way. Show that T is bounded. Or this is equivalent to say that if there exists m greater than 0 such that norm of Tx is less than equals to m of norm of x. It is in whole huge portion of function analysis. This is the way to show whether a linear transformation is whether a continuous or not. Okay, is it clear? Is it clear to everyone?
Yes, sir.
Okay. Okay. So I think this is enough for today. Try to go through the notes, whatever I am presenting today, and we will meet at next Sunday. Yeah, thank you.